angle of 45 degrees?
225.
225 degrees. And what about in the fourth quadrant?
360 minus 45.
360 minus 45, which is?
15.
15. You may notice, and these are angles that you're going to get used to, even if you don't know them yet, you will. Look at the tens digit each time. 4, 3, 2, 1. So the tens digit goes down by 1, the hundreds digit goes up by 1. Okay? But these will just be angles that you'll get used to. So, 120, 210, 300, 330, all of those are angles you'll get used to. Hopefully you'll get these quicker and quicker. What's the radian measure of 45 degrees?
Pi over
Pi over 4. That's what we were just talking about. What about 135 degrees? How many 45s
3.
is that?
3.
3?
So 3 pi.
So that would be 3 pi over 4. How many 45s is 225? 5 of them. So that's going to be 5 pi over 4.
That's 7.
How many 45s is that?
7.
7? So 7 pi over 4. So this is just something to kind of have in your pocket. You might want to write this stuff down. This will be good. This is good stuff. Because this will pop up as we go along. And we start asking about what angle, what's a 45 degree angle in the fourth quadrant? And so you start to go, all right, oh wait, look at the numerators. 1 pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Oh. So what would this be if we kept going? 9 pi over 4, 11 pi over 4, 13, 15, etc. Kind of makes it easier, doesn't it? So something to think about as you're going along. Hopefully, it may not come up right away, but as we go on over the next month or 2 months, you'll be talking about 45 degree angles in the third quadrant, and you'll go like 1, 3, 5 pi over 4. Hopefully you'll remember that. Okay. There's one more thing there. All right, questions on that? Other things that pop up. So as we start to talk about 6.6, I know that you guys saw stuff about arc length. Here we go. We're actually discussing on Friday.
Yeah.
What? Like I think I said something along the lines of, I could say, I'm going to give everybody in the class $100, and you go, oh God.
Oh, God.
I'm not going to, but that would imply that I actually have money. So let's say that we have a circle, and we have a 60 degree angle in that circle. And my question is, what's the length of that arc on the circle? What is the length of that arc on the circle? And the answer is, we have no idea. Why don't we have any idea? We have no idea how big the circle is. Right? If that circle were a unit circle, then that arc length would be big, small, medium, pretty small. If that radius were 5 miles, that would be an awfully long walk around that circle, right? So we do have to know the radius. So the arc length has to somehow be tied in with the radius, right? Okay. So they give you this formula here, but my theory, my belief in a lot of this stuff is, first of all, you guys were talking about, I think the other day, the fact that there are a lot of formulas here in this one.
Yeah.
I wholeheartedly agree. And I am not very good at remembering a lot of these formulas. Because to me, it's just as easy to logic my way through it. Okay? For instance, let's say that the radius of this circle is 5 feet. If you didn't have a formula, how would you find the length of that arc?
Oh, you have a formula? Oh, cool. Perimeter.
That's what I would do. What do you mean perimeter? What's another word for perimeter?
Circumference.
Circumference. Right, can we do Pythagorean theorem here?
No.
Why not?
Not
It's not a triangle, right? This is an arc. This is the outer edge of a pie. Okay, it's not a straight line. It is a curve. So, find the circumference. What's the circumference of this circle? How do you find circumference of a circle?
Oh, yeah.
Oh, yeah. Circumference is 2 pi r. So in this case, what would we get for the circumference?
10 pi.
10 pi. 10 pi what? Feet, right? Since we know what pi is, give me an approximation of the circumference of this circle. 31.4 feet. Is that fair? Okay. If you were trying to find the length of this arc, what would you do? 1/6 of it. Why 1/6? Because 60 degrees is 1/6 of the way around the circle. Fair? Okay. Well, the formula, okay, the formula for arc length, they call arc length S, they say it's equal to r times theta. So we can use the formula instead, which is pretty simple, because we take the r, which is 5 feet, and we multiply it by the theta, which is 60 degrees, and so we get an answer of 300 feet, which is fine, right? What do you mean?
How can the radius, how can the arc?
Oh,
Yeah.
that is a problem, isn't it?
Oh, no, you gotta put it.
The circumference of the circle is 31 feet. But the arc length of a small portion of that circle is 300 feet. That doesn't make any sense. Because
It's not in radius.
we're using 60 degrees. To use this formula, okay, please. To use this formula, theta must be in radians. So if instead of 60 degrees, we use the radian version, which is pi over 3, then we'd get an answer of 5 pi over 3. Since pi is somewhere around 3, then our answer should be somewhere around 5. If we were to divide this by 6, we'd get an arc length something like that. What's 5 times pi divided by 3? That. This is why we need radians. This is why we need radians. So, you guys, we start to talk about radians, and the question is always, well, I don't want to use radians. Can I just use degrees? And the answer...
Bless you. Bless you.
Thank you. So, this is why we need radians, because otherwise we're trying to say that the arc length is 300 feet, which makes absolutely no sense. Okay? So can we just always use degrees? Well, no. Sometimes we can convert to degrees, sometimes we just need to use radians, but we will, as time goes on, we'll use radians more and more.
So why can't you just use that the way you did it with the circumference?
So the question is, why do I need to memorize this formula? And the answer is, I'm not real good at memorizing that formula. I'm typically, a lot of the stuff that we're gonna do in this section, I don't remember the formulas, I just kind of logic it out. So my answer is, I hesitate to say you don't need to use the formula, because there will be some time that knowing the formula will be helpful. But, you know, if you get a straightforward question like this, then that's exactly what I'd do. I'd say it's, 60 degrees is 1/6 of the circumference. So the circumference is 2 pi r. So 10 pi divided by 6, 10 pi over 6. Oh wait, 10 pi over 6. Could we reduce 10 pi over 6?
Yeah.
To what?
It's 5 pi over 1.
Oh, the same thing that we got right there. Yeah. So, and it doesn't take any longer to logic it out. There are some times that it would in some types of questions. So if it's a straightforward question, that's exactly what I'm going to do. I'm not going to worry about what's the formula for that.
So they gave us the formula for degrees, but wouldn't it be easier just to convert it to radians?
Much easier. Much easier. Especially when you become more and more fluent in radians. You start to talk about 60 degrees, and if you know that 60 degrees is pi over 3, then yeah, it's a pretty simple problem, right? But yeah, that formula for... Yeah, let's see, what was that formula? Pi r theta over 180. Wow, that's an interesting one. Yeah, there's one in the book that says, oh, look at this one. Yeah, I mean, it's basically the same thing, but it certainly looks a lot more complex than that. So, and the reality is, what did they do to get this formula? Well, they're basically doing that. They're multiplying by pi over 180. So they're saying it's r times theta, but since theta's in degrees, we want to go to radians, we better multiply by pi over 180. So that's basically what they did. They just made it a bigger formula. So they're thinking, oh, why don't we just give you more and more formulas so that you have a formula for everything? My response is, I'd rather you understand what's going on, and then you're not going to need all those formulas, and you can make it much shorter. So, questions there? All right. So then we start to talk about, instead of just the arc, let's talk about the whole area in there. We call that a sector. Sector of a circle. So they start to talk about it over here. They talk about a piece of pie and stuff like that way down here at the bottom. And then, God bless you. And then we start to come over here and talk about a pizza. I like pizza. So let's talk about this question right here. Find the area of the sector associated with a single slice, with a single slice of pizza, if the entire pizza has a 14-inch diameter and the pizza is cut into 8 equal pieces. All right, so we got a couple of options here. Option number one is, here's the formula. 1/2 r squared theta.
Yeah,
All right.
let's not. Let's do that here.
How about,
Did you find the area of this circle?
say what?
Area
Just find the area of this circle.
On the area of the circle. That's exactly what I would do. Okay? Because what portion of the circle are we talking about here?
1/8.
1/8. Okay, so it sounds to me like if we find the area of the circle and divide it by 8, we should be good. Let's see if the answer makes any sense. And if the answer makes sense, then we're good to go. So where do we start? Yeah. Okay, I'm sure that's a good idea. I'm being lazy right now.
Find the area.
Area of a circle. Area of a circle? Area of a circle is pi r squared. So in this case, it is,
49 pi.
so, well, I thought it was 14.
That's the diameter.
That's the diameter. Got it. So to get the radius, we got to take half of it. So the area here is 49 pi. The area of the pizza is 49 pi. Oh, sorry. All right, now what?
Divide by 8.
Divide by 8.
Oh, I get it. Sorry. That's our
Wasn't that funny?
So
So is that our answer?
Yeah.
That's our answer. Okay. Let's use the formula. Okay? Area equals 1/2 times r squared. R is 7, you said, so 49, times theta.
In
What's theta in this case? No.
45?
No idea.
45?
45. Think about it. You don't have to do the whole 360 divided by 8 thing. Do 360 divided by 2 or divided by 4. What's 360 divided by 4? 90. And then what are you going to do from there? Divided by 2. You know what I mean? Just make your life easier. Find ways to use numbers to make your life easier. Which gives us what angle?
45.
45 degrees, which is
Theta over, pi over 4.
pi over 4. Right? Multiply across now, what do you get?
49.
Whoa. Sorry.
Cool. So, another place where the formula is nice, the formula is helpful, but it's logic. You know, you guys can do this. So, is it a bad thing to learn the formulas? Well, no. But the formulas absolutely follow exactly what you would have done anyway. Okay? Now, there are some times when you might be given different things. Maybe you're given the area and you're trying to find the angle or something like that, when it might behoove you, it's a good word for me, to actually know the formula. But in terms of the straightforward problems, you can just logic it out. Probably easier than using the formulas. Now, are we okay with that?
Yeah.
All right, that being said, there are some formulas in here that are going to be useful, and I'm going to touch on them in a minute. The next topic, or topics that they talk about here, is linear speed. The next topic is linear speed. Now, have you ever dealt with linear speed before?
Yes.
The answer is yeah, every day. Give me an example of a rate that would be used in linear speed.
60 miles per
Miles
hour.
per hour is the most obvious one that I would think is out there. Okay, when you're driving your car and you're going 60 miles per hour in a 25, no, I'm just kidding.
I'm going kilometers.
But that is a linear speed. Is it possible to have a linear speed if you are going around a circle?
Yes.
Absolutely it is. Because you can still be going feet per second, miles per hour, things like that. Okay? And you're talking about your distance divided by your time. So they give you another formula there. They say linear speed is called V. Here, let me show you this real quick.
Velocity.
Yeah, and they're calling it linear speed. But yeah, the reality is the V stands for velocity. So V is equal to S. Now what does S represent? Arc length. S is arc length. Why is S arc length? I have no idea. But it just is. Arc's length. No, I have no idea. But you just have to remember that arc length is S. So S over T. So in other words, what does arc length represent?
Distance.
Distance. So it's distance
Over time.
divided by time, which is actually exactly how you get velocity in the first place, right? Yeah, so it's all kind of tying together a little bit, all right? So we have this linear speed. The handout that I gave you, I think, calls it linear velocity. Okay, same exact thing, okay? And then they're going to change it a little bit, and they're going to go out of linear speed, and they're going to talk a little bit about what they call angular speed. Now, angular speed starts to freak you out, but it shouldn't. Because all that angular speed is talking about is what portion of the circle are you covering in a certain amount of time. So instead of being miles per hour, angular speed is going to be radians per hour, or radians per minute, or radians per second, or something like that. So if we said that you were traveling at pi over 2 radians per second, what is that saying?
Like every second.
Pi over 2.
90.
You would be going 90 degrees per second. In other words, how much of the circle? A quarter of the circle every second. How important is the size of the circle, the radius of the circle in this case? Non-important. Irrelevant. Okay? Because we're not saying how far are you going. Angular speed is saying how much of the circle are you covering. And whether it's a smaller circle or a bigger circle, doesn't matter. We're just asking about how much of the circle. And so, what is that? Yeah, what is that?
Omega.
Oh, that's an omega. That's a lowercase omega. Where does omega fit into the Greek alphabet?
C. Isn't that the letter O?
Double.
After beta, right?
It's actually
One of the
last.
last, yeah.
Yep.
Close.
Yep.
No.
Have you ever heard the phrase
Alpha. and
from the
omega.
alpha to the omega?
Yeah, first and
What's that like
From A to Z.
from A to Z? Yep. So from the alpha to the omega in the Greek alphabet is the same as saying from A to Z in our alphabet. No, how about this? We're learning non-math stuff. Well, it's in here that you learn where the word alphabet came from, right? What's the first letter of the Greek alphabet?
Alpha,
What's the second letter?
beta.
Alpha,
Beta.
beta.
28, 30.
There it is. Okay, wow, we got a lot of yapping going on today, ladies and gentlemen. Wait. Yeah, I got about 10 minutes left. Actually, I won't use that much. I'll use about 3 or 4, probably. That's it. So just stick with me for the last 3 or 4 minutes, please. Thank you. All right, so angular speed is going to be talking about radians per second rather than meters per second and things like that. So let's talk about this problem down here at the bottom. Okay, a lighthouse in the middle of a channel rotates its light in a circular motion with constant speed. If the beacon of light completes one rotation every 10 seconds, what is the angular speed of the beacon in radians per minute? Okay, that sounds like a pain, doesn't it? Okay, well let's think about this a little bit at a time, all right? Angular speed. One rotation every 10 seconds, right? But what's one rotation?
2 pi. Or
2
3.
pi. One rotation is 2 pi? So we can either just cross out the one rotation, or we could say, we could use, in science you guys talk about a unit analysis. You ever talk about that stuff?
Oh, we multiply by like.
Yeah, like think about if you try to get the units right, then you'll know exactly what you need to do, what you need to multiply by or divide by. You know, is it a multiply or a divide? What goes on the top, what goes on the bottom? Well, just pay attention to the units. Okay? So for instance, right? We want radians per minute. So we have rotations. What can we turn rotations into? Radians. So if we're going to turn rotations into radians, then we need rotations on the bottom so that it can cancel out. So if rotations goes on the bottom, then what goes on the top?
Minutes.
No. Well, we can't convert rotations to minutes, can we? But we can put radians up here, can't we? Well, we have rotations per second. So we need to get to radians per minute. That's what we want our answer to be. So we need to get a radians on top and a minutes on the bottom. Okay? So we can do how many radians are in a rotation, or how many rotations are in a radian, or something like that. And now that we have this, we'll be able to cancel rotations, and we'll be okay there. But before we do that, we got to put the numbers in this fraction. So how many radians is equal to how many rotations?
2 pi, so 1 rotation.
2 pi radians is equal to 1 rotation. Okay? Rotations are now gone, and we have radians in the numerator, which is what we want. So that's good. We have seconds in the denominator. Is that good?
No.
No, because we want minutes. So therefore, if we want minutes in the denominator, we better put minutes in the denominator. But what's going to go on top?
Rotation.
What do we want to get rid of? Right, we have rotations are gone. Because we have a rotations on the bottom, and a rotations on the top, and they cancel. So right now, what do we have? Look at what we have at this very moment. We have radians on the top, and on the bottom, we have second minutes, which makes no sense. So what don't we want?
Seconds.
The seconds. So how do we get rid of seconds?
Seconds.
Put the seconds up top. So now we know what to do. How many seconds is equal to how many minutes? 60 seconds is equal to 1 minute. And now the seconds on top cancels the seconds on the bottom, and what do we have left now? Radians over minutes. Radians per minute. And so we have what we want. How do we get our answer here? We multiply straight across or cancel if we want. Like for instance, I like to say that 10 goes into 66 times, which gives us 12 pi. And there's our answer. The unit analysis, I almost said item analysis. The unit analysis is something that once it clicks to you, it will make a lot of problems easier. And so when you're doing some of these problems in your homework, try to use this. Because I promise you, in the grand scheme of things, it will help. All right? I'm trying to get radians per minute. I have rotations per second. Well, I know how to get from seconds to minutes. Okay, I can just multiply by 60 seconds. 1 minute. Seconds cancel. We're good there. And then, so now, just like we talked about. But try this. Okay? I think it will help. All right? Questions there? Okay, I got one more thing. I'm sorry. That took longer than I thought. I apologize. But here's the last thing. And that is down here, and they talk about relating linear and angular speeds. Okay. This is the formula that you want to know. This is the formula that I wish I remembered more often. Because they're going to be talking about angular speeds and how do you get to linear speeds and stuff like that. And so what I typically do is I end up doing like 4 or 5 steps using this unit analysis thing, and I eventually get there. Boy, it's a pain. And it would be so much easier to just remember that what does this represent? Also known as linear speed, is equal to the radius times omega, which is angular speed. So linear speed is equal to radius times angular speed. Wow, that's so much easier than the way I usually end up doing it. I usually end up having like 4 or 5 things multiplied together, and I'm like, it has to be easier than this. This is radius, okay? Omega would be in radians per second, radians per minute or something like that. So the radian stuff is going to come into play with the omega. Now we can just change this around and get omega equals V over R. We can do it that way. These 2 formulas are nice to know, and they will make your life a lot easier if you can remember to use them. So. Look at this. Notice the tires of 2 different radii with the same angular speed have different linear speeds. Wait a minute. What does that mean?
You change the tires on the car and it still moves up the same pace.
That means if you change a tire on a car, it might be a pain if you put on a tire that's a different size. Because the tires, because they're attached to the axle, will always go at the same angular speed. Right? They'll go at the same angular speed, but the bigger tire will be going further than the smaller tire will, even though you're going, they're moving at the same angular speed. Does that make any sense? Which means, don't put on a tire that's a different size.
Making
Because
me
you'd be
physics,
like
it's making
driving
me
like
read.
this just to stay straight down the road or something like that. Questions?